Hello everybody, and welcome to page 14 in the workbook. And on this page, we're going to describe a general strategy for taking a rational function, that's something that looks like p of x over q of x, and breaking it into its partial fractions decomposition. We used this technique in the example on the previous page when we integrated the function 2 over x minus 1 times x plus 1. So being able to take a function and break it into smaller pieces is a helpful tool for integrating. Okay, and it turns out that finding the partial fractions decomposition is all about looking at the denominator and what factors are going on there. Okay, so this table that we're about to work through together describes three different cases to us. And notice that all three of the cases have to do with the denominator. It's telling us what to do based on what we see in the denominator q of x. Okay, so let's start with the first two cases here. Notice that they talk about linear factors. Okay, x minus c is a linear factor because x is being raised to the first power in both of those two situations. Okay, and if we discuss those two separately, the first case up here says if our denominator just contains a single factor that looks like x minus c, we just need one term in our partial fractions decomposition, a number a, over that factor x minus c. Okay, if on the other hand it turns out that we have a linear factor that's repeated, okay, and by repeated we just mean it's raised to the nth power, it's occurring n times, turns out that we need a whole list of terms in our partial fractions decomposition. Notice that we're starting with a constant over x minus c, and we're continuing until we get to x minus c to the nth. It's like one term for every power up until n. Okay, and then finally, what would happen if we had something that's not linear? That's what the third case is all about. Okay, so if we have a factor that's quadratic, x squared plus cx plus d, that's irreducible, that just means that we can't factor it, then we basically get the same types of situations that we did above, with the one change that instead of constants in the top, we're going to have terms that look like ax plus b. Okay, now this is a lot of information to take in at once. This chart has a lot of information, and so to make sense out of it all, we're going to work through a number of examples just so we can see what these cases really mean. All right, so looking at example 2, they'd like us to take each of these functions and define the form of the partial fractions decomposition. So we just want to break the function into its various parts, not worry about solving for the constants. Let's start with part A, which gives us a function that looks like 3x over x plus 1 times x minus 2 squared. Okay, the idea is to look at the denominator and to ask ourselves what kind of terms we see. So if you start with x plus 1, that's x to the first power plus 1. That's just a linear factor. It's not repeated because it's just x plus 1. And our chart tells us that we just need one term for something like that. A over x plus 1. Okay, on the other hand, if you look at the second term, the x minus 2 squared, x minus 2 is being raised to the second power, so it's repeated. Okay, and because it's repeated, we actually need two terms for it. An x minus 2 and an x minus 2 squared. Okay, and in the top we need two constants, which I'll call b and c. Okay, so those three terms together give us the linear fractions decomposition, or I'm sorry, the partial fractions decomposition of our function. Okay, and we're done with A. Okay, so moving on to part B, notice that that function is similar to what we did in part A. 3x over x plus 1 times x minus 2 cubed. So we start off with the same linear factor, okay, x plus 1, and so we're going to get exactly the same first term in our decomposition, a over x plus 1. And when we move on to x minus 2 cubed, that's also a repeated linear, but it's repeated 3 times because of the third power. That just tells us that we need 3 terms So x minus 2, x minus 2 squared, and x minus 2 cubed, and then we need a new constant for each one, so a b, c, and a d. Okay, and that's what our answer would look like. Okay, and then moving on, what about c here? Okay, well, here's our first example of a quadratic term, x squared plus 1. That's got a power of 2 on it, and we can't factor it. X squared plus 1 does not break down. So this is what we call an irreducible quadratic factor. Okay, so how does that work? Well, according to the table, because that's quadratic, instead of just putting a constant over the top of it, we need to put an ax plus b over the top of it. That's the difference between a linear and a quadratic factor. Okay, and then moving on to the second term, x minus 2, that's linear. X is being raised to the first power, so there we have one term and all we need is just a single constant, c. We don't need a cx plus d because x minus 2 is linear. Okay, and there's our decomposition. Okay, and then moving on to d, let's see what's going on there. Okay, when you look at the first term, x squared plus 9, you might look at that and think that's a quadratic factor. Well, you're right, it is quadratic, but it's not irreducible. We can factor it, we can break it down. And it's important that we do that if it's possible. X squared minus 9 actually factors as x minus 3 times x plus 3, so we're going to do that first. And so really, what we've got going on in the denominator are just 3 linear factors, x minus 3, x plus 3, and x minus 2. So we just need one term for each of those. Okay, and what do you think belongs in the numerator? Well, because all of those are linear, we just need an a, b, and a c. No x's upstairs because all of our factors are linear. Okay, and finally, moving on to part E here. All right, so looking at the denominator, this kind of an unusual thing going on here, x squared, I want to remind you that that's really just another way of writing x minus 0 squared. Okay, by rewriting it like that, it's maybe a little easier to recognize this as a repeated linear that we're looking at. X minus 0 squared. So, because it's repeated, we need two terms, x minus 0 and x minus 0 squared. And the fact that it's linear tells us that we just need an a and a b in the top. Okay, and then we move on to the x squared plus 1 squared. X squared plus 1 is an irreducible quadratic and it's repeated because of the squared outside. So we'll call it a repeated irreducible quadratic. Okay, so because it's repeated, we actually need two terms, x squared plus 1 and x squared plus 1 squared. And what do you think is going to go in the numerator this time? Okay, well, because x squared plus 1 is a quadratic, we actually need not just a number, but a cx plus d and an ex plus f. Okay, and there's our decomposition. Okay, and just as a closing remark here, in theory, for any of these problems, we could algebraically solve for the constants that are in the numerator, but they told us not to. Okay, and in fact, some of these would be really difficult because there are so many constants. We'd have to do a lot of algebra if we wanted to do that extra step.